All right, hi everybody. This is actually my second attempt at this video. In my first video, I kind of did things out of order and I realized that I should change things up a little bit. So I'm actually going to walk you through this in a little bit different manner than I have in the previous. I'm going to be looking at my notes pretty closely because I don't want this to be that confusing. All right, so today we're going to cover the section 3 of chapter 17, practice problem on pH at the equivalence point. And in order to do this, we have to realize a few things. So first off is the given problem. We're told the pH, we want to know the pH of the equivalence point in the titration of a weak acid with a strong base. Now, what that means is that we're looking at an equation like this one initially. Okay. Now, this is not actually what's going to end up happening. What's going to end up happening is the inverse of this. And so one of the things I did was I kind of tried to write this out and showed you, is this the Ka question mark? Well, yeah, but that's not exactly what we want. And in fact, what we're going to end up doing is flipping this equation to have the conjugate base on the left side added to water to give us the acid in the base. And there's a reason for that, but one of the reasons we're going to do that is so that we can actually use the Kb instead of the Ka. Now, in order to do this problem, one of the things we have to do first is figure out some molar information. So, knowing that this is how the reaction actually occurs. Okay, so first thing to know is we are starting with 50 mils or 0.05 liters of the acid. Oops, excuse me. And oh my goodness, at a strength, of 0.100 molar. We can calculate how many moles, as we've done in a previous video, or many videos, by taking the volume times the molarity and getting a molar amount. And this is going to give us the initial of the CH3COOH. Now, at the equivalence point, we know the moles of acid must equal the moles of the base. Okay, so if we know that this is the moles of the acid that's been added, we know that this is also the moles of base. Okay, by definition, that is what an equivalence point is. So we are going to try to figure out what the volume is that would give us that. Of the 0.1 molar NaOH would give us 5 times 10 to the negative third moles of NaOH. This is our next part of the problem. All right. So in order to figure this out, remember the formula we've been using, and it's not really a formula, it's just kind of a general how units will cancel. It gives us the number of moles. Well, if we want to know what the volume is, we just divide by molarity. So we're going to get that volume will equal moles over molarity, which for our sake is going to be this calculation. So the volume is actually going to end up being the same exact volume as it was before. Okay, so now we did that so we could get V total. And I'll show you why this is going to matter in a a second. Okay. All right, I'm going to erase some stuff so we can move on. And I know I might be moving kind of fast, but you have the ability to pause. So there's that. All right. All right. Now we have V total at 100 milliliters. What we want to know is what is the molarity, our next step, sorry, of the conjugate base with both present. So in other words, when we add the acid and the base together, what is the molarity of what's going to be present on the right side of this reaction? In other words, we're going to take that we know that this had 5 times 10 to the negative third moles present, right? We know that this is a 1-to-1 reaction, so if I have that, I know I also have that as well. So I'm going to take that number of moles I'm going to divide it by the V total in liters, which is going to be 0.100 liters. That's what 100 milliliters is in liters. And I'm going to get that the concentration of the conjugate base is going to be 0.0500 molar. All right. Okay, so now just kind of let's go through this mentally. We added this weak acid to this weak base. At equivalence, they've reacted, and the only thing left over is this. Okay, so what we're going to do with this information is we're going to actually go back and we're going to treat that like it is there by itself. So we're actually going to invert the equation. And we're going to say that at the equivalence point, this is what's happening. We have the conjugate base with water. When those two things react, the water is going to be the acid and give a proton to our base. So we're going to get our conjugate acid and our conjugate base. Now, this particular equation has a KB. And if we wrote out an expression for KB, we would write, remember products over reactants, and remember that we always ignore water. This is what we would write, okay? And if we were at equilibrium, we know that that KB would also have a value. Now, we were given a Ka at the beginning of the problem. What can we do with that Ka to get it into a KB? If you said that we could get a KB by using the Kw formula, you're correct. For us, don't forget that the Kw is a constant, and the Ka, which was given, can be used to get ourselves a Kb. And trying to get it go down. Trying to get it down and all over. I'm sorry. I'm new to the OneNote thing. It's been going pretty well, I think. Whatever. All right, so our Kb then comes out to be 5.6, if you do it in your calculator, times 10 to the negative 10th. Okay, so I'm going to clean some of this up real quick. what I'm going to do is I'm going to erase some of this. We know this value at the bottom. I'm assembling our information just in a... I wish I knew how to like move stuff and not just like erase it, but you know what? Maybe I'll learn that soon. You never know. And this is going to be, we just did this. 5.0 times 10 to the negative second. Did I get that right? I just want to make sure that that is what I definitely had written down before. Okay, so here we are. We got lots going on. I'm sorry we have lots going on the screen. Cleaning it up. Okay, so we still have our equation at the equivalence point down here at the bottom. I'm going to use that moving forward. I like this KB that's already set up. I know the value for KB is that 5.6 times 10 to the negative 10th. So next thing I'm going to do is realize that if I had an ice table, okay, now think about if I had an ice table. I'm going to try to cut this. Ooh, look what I did. Ah, I'm fantastic. Proud of myself. Think about if I had an ice table, what would happen? I would have come back to me, C, E. And you've seen these before. These are not new. Please don't pretend like they're new to you. We're going to fill in what we know. And at equilibrium, we know the concentration of this guy is that 0.05 molar. We also know that in theory, that is where we would start, right? And so our change would be 0.05 minus x. We would have nothing in this column, don't forget. And if we were subtracting from the left side, we'd be adding to the right side always. Remember, you can't subtract a concentration from zero. You can't have negative concentrations. That hopefully makes finite sense to you at this point. We can subtract from values that do exist. So over here, this becomes 0.05 minus x. This becomes x at equilibrium and x at equilibrium. All right. Hopefully you see exactly where we're going next. We have an expression for KB. We have stuff at equilibrium for KB. We're going to plug it all in and see what we get. Okay, so we're going to do the 5. And remember that with your expression, this is essentially what happens. Now, quick reminder, can we ignore this x? Given that KB is so small, let's ignore it for now. My guess is it won't matter. If you want to solve it with x, please feel free. But my guess is it won't come out with a value very much higher or any different than the x that we're going to end up getting by ignoring it. And we can prove this to ourselves, I'll remind you, by going back and looking at our x at the end. If our x value is so small that it doesn't actually impact this concentration, then we know we're in the clear and it's okay that we ignored it. All right, so we're going to solve this problem for x. When you do that, you should get a value of something in the neighborhood of 5.3 times 10 to the negative 6th molar. Okay, from here, we want to find a pH, right? But for now, do you remember that x from our KB expression represents an OH minus? So we can't directly calculate a pH, but we can indirectly calculate a pH by doing the POH thing that we've done before. So we're going to take that. I'm going to do POH. It's the negative log of the concentration of OH minus, which for us is going to be the negative log 0.3 times 10 to the negative 6. Just a quick reminder that, remember we said we could go back and we could look, our x is so small, if we tried to subtract this value from this value, so if we did 0.05 minus 5.3 times 10 to the negative 6th, our value would still round to 0.05. It would come out to be like 0.04999. So yeah, we can ignore x in this particular problem, and we can feel good about ignoring x because this value is so much different. All right, that gives us a POH of 5.28. Remember that to get pH, we can take 14 minus POH, And in doing that, we will get our pH of 8.72. Okay, so let's do some quick analysis. Does our answer make sense? Let's go back up to our question. It says that we are taking a weak acid and we are titrating it with a strong base. We know in this particular situation, equivalence pHs, and this is something that's in our reading, will be greater than 7 for this situation. So in other words, our pH of 8.72 makes sense. Woo! All right, nice job. Okay, so for what's next, I'm gonna just erase this real fast so it's not in your way. Remember that your next task is to actually do your own problems. Okay, here are your turn problems. I'd like you to do these and I'd like you to submit them as proof that you watched this video and you understand what's going on. Thanks, guys.